Okay, so welcome to class on Monday the 15th. The plan for today is to cover 16.5 curl and divergence. The supplement for this week, 16.6 on parametric surfaces and areas. And then Wednesday's class 16.7 on surface integrals. We had a short discussion on the plan for next week as well for week 10. And Monday, we're going to cover Stokes' theorem. Wednesday, we're going to consider the time that would be allocated to class time on Wednesday. That's the time we're allocating to the final exam. And 16.9 on divergence theorem will be a supplement posted. That will be posted at the latest on Monday the 22nd, and that'll be available for you. Note that 16.8 Stokes and 16.9 divergence theorem are not on the final exam. The final exam is only through this week's material. That gives you a little bit of a buffer to study and to get some of the material under your belt before taking the exam. The final exam will be available this coming Friday, the 19th at 9 a.m. And it will be available through the following Friday, the 26th. Note that it's due on Friday, not the typical Sunday, because of the way the semester ends. And as always, I strongly recommend that you plan to take the exam at least a couple of days ahead of time, ahead of the final due date, because there are no due date extensions. And even if there is a very extenuating circumstance, due date extensions are quite a bit more cumbersome at the end of the semester, just because of grade submission deadlines, things like that. And of course, getting credits transferred, getting prepped for your classes for fall, approval for any coursework that might depend on this course, anything like that needs to turn around pretty quickly at the end of summer. So definitely plan to take the exam a couple days before the 26th, so you have a nice buffer there. Okay, we are now going into the material for 16.5 curl and divergence. So we're going to start a little bit differently than how the book approaches it. We're going to start in the two-dimensional case, and then we're going to move to the three-dimensional case. And we'll see that there's a little bit of a shortcoming in part of the two-dimensional case that we're going to discuss, but I think this is the more natural way to present the material, even if it's not the most linear from kind of a mathematics standpoint after you know all the material. If you know all the material, it makes sense to present it a little bit differently, but as you're discovering the material, I think this is the more sensible way. So that's why I'm deviating from Stuart a little bit here in the way I develop this. So what are the basic ideas of curl and divergence? Well, we have this idea of a vector field. And so we have F bar and maybe 2 or 3 dimensions. And we might be interested in something like the derivative of a vector field. So how can we take the derivative of a vector field? Well, essentially, curl and divergence are 2 different types of first derivatives of a vector field. We've already seen a way that a derivative kind of relates, in a sense, to a vector field, that we might have gradient of little f, gradient of a scalar function equals big F. So I know that a vector field can itself be the derivative of a scalar function in a sense. It can be a gradient field. But here I'm asking, if I have a vector field and I want to take its derivative, what does that look like? And there are kind of 2 types of first derivatives, the curl and the divergence. As derivatives, these are local properties of the field. So this is a property that would exist at each point in the field, right? Our vector field has points as inputs, maybe say here a 2-dimensional point as input, and it gives us an output, a 2-dimensional vector. That's what the field does. And local to that point in that vector, there's maybe an idea of curl and an idea of divergence that both are in some sense first derivatives of this vector field. So just kind of conceptually, what do these ideas mean? Well, the idea of divergence is actually a little bit obvious from the word itself. It's the tendency of the field to flow away from the given point. So again, this is a local phenomenon. And if I imagine that I have some kind of water, often we think of vector fields as representing kind of fluid flow. Or maybe even better in this case is, say, a gas, because gas can be compressed or it can be expanded. So if I'm looking at a certain point and my gas is heating up and expanding, and if the gas is kind of flowing away from that point, the molecules of gas tend to be flowing away from the point more than they're flowing toward it. That would be divergence. So I say positive divergence indicates flowing away from a point, or I can kind of think of, if I was thinking of a two-dimensional, say, water table, like a thin sheet of water on top of a table, maybe this would be like where there's a little faucet that's adding water into the table and pushing the water away from that point. It's maybe a source of more water or of more whatever it is that my field is describing. A negative divergence in the gas sense would be like gas kind of collapsing in and coming towards that point, maybe cooling down. Or it might be like a drain in a water table where there's a lot of water kind of coming into a certain point, and not a lot of water going out, where the flow is more inward, indicating a sink or kind of a loss of material there. Curl is a little more difficult to define. It's, in a sense, the tendency for a field to rotate about a given point. And the way that I like to kind of think of this is, if you've ever seen one of these before, this is called a Crookes radiometer. I didn't remember what it was called until I looked it up. Or it's just one of these little light spinny things. Basically, you have a tube here that's a vacuum, or very near to a vacuum. And inside of it, you have this little paddle wheel. The paddle wheels on one of the sides are white and the other side are black. And when light hits it, it bounces off. And I feel like it should bounce off of the white and be absorbed by the black and kind of spin in the direction where the black comes toward you and the white goes away. But I would have to think about that for a minute. I feel like there's something counterintuitive there. But anyway, the light hits this and kind of causes it to spin. And that's what I kind of think about when I think about curl. I think of imagining that this vector field represents fluid flow, let's say the flow of some water or perhaps the flow of some air. And I put a little paddle wheel like this at a certain point in that fluid. And then I ask, as that fluid is pushing against those little veins, which way does it tend to rotate that paddle wheel, or does it tend to not rotate it at all? So the tendency for the field to rotate about a given point is the curl. The sign, so to speak, is determined by the right-hand rule. So if it would tend to rotate counterclockwise from this two-dimensional perspective, in other words, if I take my right hand in kind of the natural position, not some kind of crazy backwards position, and I rotate my fingers around counterclockwise for my right hand, my thumb points towards me. If my field would tend to rotate that little propeller that direction, I would say the curl is positive. And if it's opposite that direction, I'd say it's negative. We'll see that this definition of curl is a little bit wanting when we get to 3 dimensions, but we'll handle that at a later point. So let's take a look at 6 different vector fields here and decide, just roughly speaking, whether we think that for most points in the vector field, the divergence is positive, negative, or 0, and the curl is positive, negative, or 0. So for my first vector field up here, I see that I have this kind of rotational field. It's the whole thing is kind of rotating in a counterclockwise way. That might give me a clue for curl. If I put such a weather vane in the middle here, or I guess not a weather vane, but whatever kind of vane it is, in the middle here, the field is going to tend to hit my little vanes in this direction and cause, of course, a counterclockwise rotation, giving me a positive curl near the origin. Now, I do recognize that curl is a local property. So the curl at one point could be different than the curl at another point. So maybe I want to take a couple of different sample points. If I think out here, well, out here I kind of have a situation that's a little less clear, because I have vectors on the, let's say, top left vane pushing and wanting to rotate it counterclockwise, but I have some vectors on the bottom right vane that are pushing and tending to want to rotate it clockwise. So they're kind of counteracting one another, and maybe on the other vanes, these are roughly parallel to the vector, so they don't have much of an influence. So one thing I have to be a little bit careful about with curl is the fact that the vector field I'm looking at, the representation I have, is it scaled or not? We said that, sometimes vector fields, when they're visualized, sometimes they scale all the vectors to a certain length. Well, here I was careful not to do that. And we see that these vectors, I'm going to exaggerate it, on the top left are bigger than these vectors on the bottom right. So even though they're counteracting one another a little bit, still the top left is going to push much harder than the bottom right. And overall, we're going to get a counterclockwise rotation here as well. And the same thing could be said, for instance, over here, the vectors on the top right over here are pushing much harder than the vectors on the bottom left. This is still going to cause a counterclockwise rotation. The top right wins out and makes it rotate counterclockwise. And I can see that that would essentially be the case pretty much anywhere, well, really anywhere in this field. Most places in this field, we have some, force and counterforce, but the clockwise impetus that's counteracting is not as strong as the counterclockwise impetus. So we're going to get a counterclockwise rotation, it seems like, everywhere in the field. So we should get a positive number for our curl. Now, what about divergence? I mean, I guess divergence, again, it's really a local property. It's a property at a point. It's really hard to visualize what's happening at a point, though. So typically what we would do is we would draw, say, a little circle or perhaps a little box. And I would imagine the vectors going in across the boundary of the circle and the vectors going out across the boundary of the circle. And I would kind of ask, does it seem like the vectors going in are bigger than the ones coming out right at that boundary? If so, it seems like there's a net inward flux, inward flow, maybe a negative divergence. Or does it seem like the vectors going out across the boundary are bigger than the ones coming in which case maybe there's a net outward flux, a net outward flow, a positive divergence. And if I look in this picture, if I draw a circle pretty much anywhere here, I can see that the inward and outward flux is pretty much balanced. I have, for instance, this vector kind of near the boundary coming in, but I have essentially an equivalent one coming out. I have this vector, it's a little bigger than the previous one I looked at coming in, but I have one basically matching it perfectly coming out. Same thing over here. Same thing down here. It kind of seems like for any little circle that I draw somewhere on this picture, the kind of inflow and the outflow perfectly match. And if I draw a circle, I would want to draw a little circle, but I'm going to draw it a little bigger because my little weather vane thing is in the way. If I draw a circle centered at the origin, I actually get seemingly no flow across the boundary. The stuff on the inside just swirls around and stays inside, and the stuff on the outside swirls around and stays outside. At least, we're visually estimating here, but that's what it seems like. So it seems like there's not really a net inflow or outflow into any little circle. I think my divergence is probably 0 at any point in this field. Now, as I mentioned before, I could certainly have a field where the divergence is 0 here and positive there and negative there, but we're starting with simple fields so that we can get an idea about how these ideas of curl and divergence relate to the geometry of vector fields. Okay, so let's do another one. This is pretty much the same vector field, except it's kind of spiraling in the opposite direction. Again, my divergence I suspect is 0 for the same reasons I outlined above. My curl now at 0, of course, it's rotating clockwise away from 0, away from the origin. Again, I have some kind of competing forces, but it seems like the ones on the outside always outweigh, always outpush the ones on the inside and lead to a clockwise rotation. So it looks like pretty much wherever I put one of these little these little weather vane kind of things, it seems like they're always going to rotate clockwise. So I would expect a negative curl here. Remember, kind of related to the right hand rule and related to like Green's theorem and the way that we positively orient a curve. Counterclockwise is positive and clockwise is negative. So um, unfortunately, that's just how we decided to make math. We prefer counterclockwise over clockwise for whatever reason. Okay, now if I look at a field like this where I kind of have everything seemingly going away from 0, away from the origin. Well, here if I, oh, wrong figure, if I put a little weather vane somewhere, I see for the kind of top left to bottom right line for those two vanes, those are parallel to the vectors for the most part. Nothing's really pushing against them. I have some vectors pushing against this bottom left piece and against the top right piece. But in this case, it looks like they're pretty well balanced out. And it looks like that pretty much anywhere I put my little weather vane. And I'm kind of intentionally trying to line one of the lines up with to be kind of parallel with the vectors because it makes it a little easier to interpret. I see that anywhere that I do that, it seems like I have about an equal push on one side versus the other. So I'm not really rotating clockwise or counterclockwise. My little weather vane is just kind of sitting still. I think my curl here is going to be 0, probably at any point in this vector field. On the other hand, if I think of my divergence, well, of course, if I think of the origin and I put a circle there, I have vectors that are leaving. It's a little hard to see them because they're scaled, they're kind of really short near the origins. Otherwise, they would just all start overlapping each other. You want to be able to see the vectors very well. But I can see that there are lots of vectors pointing out away from the origin, going through the boundary of this circle outwards, but nothing really going inwards. So near the origin, my divergence is kind of going outwards. My divergence is positive. It's diverging away from that point. Is that just at 0 or does that happen kind of everywhere? Well, if I look at a circle out here, again, I would think of this as being a pretty small circle, but I'm drawing it bigger for illustration purposes. Well, here it's a little less clear because I have some vectors, namely kind of on the top right of the circle, that are flowing in, that are kind of going in towards the quote sink, maybe making it act like a sink in that direction. But I have other vectors coming out, making it act like a source in that direction. So there are countervailing forces. But I note that the vectors coming in are much smaller than the vectors going out. So I have a little bit of flow into the circle and a lot of flow out of the circle. That's a net outward flow. Since I have a net outward flow, I think my divergence is going to be positive, not just at the origin, but it seems like basically anywhere. My vectors flowing into the circle are smaller than the vectors flowing out of the circle, so my divergence is positive. I get a net outward flow. And just kind of the opposite here. This is a similar vector field, but everything is flowing in towards the origin. I see I have big vectors flowing in, small vectors flowing out, so net for my divergence, my net is an inward flow. Divergence is positive when we're diverging when we're going out, so it's negative when we're going in. I expect my divergence to be a negative number at most points here, at points like these. And of course, at the origin too, that's kind of a special case, but I see it very clearly. If I take a circle centered at the origin, then all of the vectors are pointing in. And then there's no question at all that this is definitely a sink. It's a point of negative divergence. And then curl, for the same reason as above, I would expect to be 0. I have very nice counterbalancing of the forces tending to make my weather vane want to rotate clockwise versus counterclockwise. Okay, then let's look at these two. These can be kind of tricky because, right, these two examples up here where the curl was non-zero, the field seemed to as a whole rotate, like it looks like it rotates. These two fields where my divergence was non-zero, it seems like there's stuff flowing out from a certain point or flowing into a certain point. But fields like these, it can be a little hard to immediately grasp what's going on here. So this is where those ideas of drawing the weather vanes or drawing the circles, where that really helps. What colors was I using? Green for divergence, okay. So if I look at divergence and I draw a circle, say over here, or maybe somewhere over here, well, I note that I have some inflow and some outflow, and it tends to be balanced. Near the right half of the circle, I have larger inflows, but also equally large outflows. And near the left half of the circle, smaller inflows, but also smaller outflows. And similarly over here. It's a little hard to see once we get near the y-axis, but basically the same thing is happening on a smaller scale. I think my divergence of this field is going to be 0. Seems like anywhere that I draw a little circle, there's about as much inflow as there is outflow. And here's where it can get tricky. We might look at this and say, oh, I think the curl is 0 because it doesn't seem like the field as a whole is rotating. But we have to be careful. Remember, these ideas of divergence and curl, they're not properties of the whole field. I mean, it did happen to be the case that, in a sense, these whole fields were rotating, so it made it kind of obvious that the curl was going to be non-zero. But down here, curl is a pointwise property. It's a local property. It's not zooming out and looking at the whole field. If I put a little kind of weather vane kind of thing in here, and again, I line up one of the axes parallel to the vectors, I note that my field is pushing a lot harder on the right side than it's pushing on the left side. The vectors on the right side here are a lot bigger than the left side. This is going to cause a rotation this way, a counterclockwise rotation. And if I move it up or down, of course, everything is translationally symmetric up and down. If I move it left or right, well, if I stay on the right side, things basically stay the same, just with different magnitudes. If I jump over to the left side, does anything change? Well, here I have bigger forces on the left side and smaller on the right side, but they're pushing in the opposite direction. It still tends to rotate counterclockwise. I would actually expect a positive curl at any point in this field, even though the field as a whole doesn't look like it's rotating. But if I think of like having something like a river, or maybe this is like the opposite of a river kind of flows faster in the middle and slower near the banks, but this is going faster near the outside and slow in the middle, and it's going in two different directions on one side versus the other. That gives me a curl. And one little note, even if I had something closer to like a river, where I had lots of flow in the middle, less flow out here, and very little flow further out, Again, if I put a weather vane, say over here, or if I put a weather vane over here, I'm going to get a non-zero curl. In this field, it's going to be a little different depending on what side I'm on. So this isn't the best basic example, but even in something like a river where everything is flowing the same direction, I still get a curl. The curl being non-zero is not coming from the fact that the two sides of the field are flowing in opposite directions. That's a global property. It's coming from this local phenomenon that nearby vectors are different magnitudes. So even in something like a river where all the water is flowing the same direction, but at different speeds at different points, I would still get a curl at most points. I suppose if I was right in the middle here, things would kind of balance out and I'd get zero for the curl, but I would get positive here, negative there. So just a little side note there. It's not the global property of the kind of shearing, the two sides going different directions. It's the local property of the different magnitudes of the vectors that's giving rise to a non-zero curl. Okay, now what about down here? Well, now if I investigate curl, I see that my kind of my pushing on one side is perfectly counteracted by a pushing on the other side. I don't tend to rotate either direction. I tend to just stay pretty stable wherever I put my little propeller in here. So I think my curl here ends up being zero. Again, not because the whole field doesn't seem to be rotating, but because at each point, there's kind of a balance in the magnitudes of the forces. What about my divergence? Well, if I look at somewhere like up here, I draw, again, I would imagine this being a very small circle, but so we can see it, I'm drawing it bigger. I do notice that along the top half of the circle, the outflow vectors are quite large relative to the inflow vectors near the bottom. It seems like there's a net outflow in a circle like this, or a net positive divergence here. This would be the same here or here. Is it the same down here? Well, down here, I actually have something different, right? I have the bigger vectors are inflow vectors and the smaller vectors are the outflow vectors. So I have a net inflow, or I have a negative divergence down here. This is my x-axis, y equals 0. So it kind of seems like for my divergence, remember, divergence and curl are pointwise properties. So far, we've been kind of applying them to the whole vector field. I've picked vector fields up to this point where the sign or the zero property doesn't change across the whole vector field to make it simpler. But we do see in a vector field like this that even with everything kind of pointing upwards, divergence seems like it's going to be positive for y bigger than 0 and negative for y less than 0. But it does seem like the curl is going to be 0 everywhere. And if I'm right at y equals 0, it kind of seems like the inflow and outflow is balanced, so probably 0 at y equals 0. So I think it's really beneficial to go through something like this and just look at the vector fields, try to pick a couple different points, get an idea of whether you think the divergence and curl are going to be positive, 0, or negative. I think that gives you a lot of intuition as to how this applies to vector fields. One of the really big takeaways is that these are pointwise properties, not properties of the whole fields, as really shown here, that even though the whole field doesn't seem to be rotating, or even more clearly shown over here, the curl is still non-zero. Okay, so let's Let's discuss a couple definitions then. So we say the curl of f of xy, and really this is kind of a two-dimensional analog of the actual curl. So this isn't quite a curl, but we're just going to call it the curl now, the two-dimensional analog of the curl of vector field f of xy being p comma q is defined to be curl f is dq dx minus dp dy. Again, why this break in symmetry? Why do we have one of them coming in positive and one of them coming in negative? Well, that's because of our choice to use the right-hand rule. Right, it's our choice to make the counterclockwise the positive direction and the clockwise the negative. If we had chosen the opposite convention, we would have got the opposite orientation here as well. And the divergence of f of xy, and this really is a divergence. We don't, the curl is a little bit wonky, but the divergence works just fine in 2D. The divergence of f equals pq is the partial of p with respect to x plus partial q with respect to y. So note that the curl, kind of like in Green's theorem, the derivatives kind of mix with the coordinates, right? Kind of the x coordinate of f gets the y derivative and the y coordinate gets the x derivative, where in the divergence, they kind of stay consistent. The x coordinate gets the x derivative, the y coordinate gets the y derivative. And you might even look at this and say, like, this almost feels like a gradient somehow. You know, this divergence kind of has a similar feeling, at least to me anyway, as like a gradient. The curl is kind of its own wonky thing. At least that's my gut feeling. Okay, so now we looked at each of these vector fields kind of geometrically. Now let's take these algebraic definitions and look at each of them algebraically. These are the functions that give rise to those same vector fields up above. So looking back at A and B, this was the counterclockwise rotating whole field and the clockwise rotating whole field. And for A, we thought the curl was positive, divergence 0, and for B, curl negative, divergence 0. So I thought that the divergence was 0 in both, and I thought that the curl was positive versus negative. So these were my guesses from my visual intuition. Let's actually compute them. So the divergence of f, we can just write it div of f. Well, that is partial of p with respect to x. So the partial of negative y with respect to x plus the partial of q with respect to y. Divergence is 0 as we predicted. Oh, and there we go. And similarly for b, the divergence of f, again, partial of p with respect to x, well, p has no x's in it. So 0 plus partial of q with respect to y, 0 is also 0, as we expected. For A, what's the curl? Again, it's dq dx minus dp dy. So it's the partial of x with respect to x is 1 minus dp dy is minus 1. 1 plus 1 is 2. This is positive. Let me just write it like this. As we also expected. Now, something to keep in mind that, again, the curl is a pointwise property. It's not a property of the whole vector field. But I happen to choose vector fields here where across the entire vector field, the divergence is 0 and the curl is 2. So for any point you pick, we happen to get a divergence of 0 and a curl of 2 at whatever point for that vector field. It's kind of, in a sense, like if you differentiate and get a constant, then the value of your derivative, like in Calc 1, the value of your derivative doesn't change with the input. Same kind of idea here. This is in some sense what like a constant derivative field analog would kind of look like. And then again, the curl for part B, curl F, well, again, that's from up here, dq dx, derivative of this with respect to x is -1 minus dp dy. So minus a +1 is -2. That's negative, as we expected. Again, in part B, this was a simple example. Simple in the sense that, in the sense of the mathematics, not necessarily in the sense of the ideas. But the divergence and curl for the field in part B are also the same numbers everywhere. Whatever point you choose to look at, the divergence is 0, the curl is -2. Okay, what about C and D? Well, here we expected over the whole field that the curl was 0 for both of them, and the divergence was positive for C and negative for D. So here I thought curl was 0 in both cases, and the divergence was positive in the first case and negative in the second. That was my prediction. So let's check it. Well, the curl dp dx, well, dy dx, that y doesn't have any x's in it. That's 0 minus, or did I say dp dx? dq dx minus dp dy. And similarly down here, we get 0 minus 0 equals 0. Q doesn't have any x's in it. The second component doesn't have any x's. The first component doesn't have any y's. So our curl in both cases ends up being 0. And the divergence for the first one, dp dx, the derivative of the first with respect to x is 1, plus derivative of second with respect to y is 1. The divergence is 2, it's positive. Again, it's the same number at any point in the field. It just, we picked a simple field to work with. And part D, dp dx is -1 plus dq dy is -1, -2 is negative, as we expected. Okay, and then E and F. So for E, I think my divergence is 0 and curl is positive. Let me write that down. That's my prediction. And this was the field 0, x. So the x component of the vector is always 0. We never, our vector never points to the right or left at all. And the y component is just x. So when x is more positive, we point further up. And when it's more negative, we point further down. So that was the field E. And then for F, we thought the curl was 0 and the divergence was positive for positive y's and negative for negative y's. So that was our prediction here. And this field is 0 for the x component. Again, our vectors only point up and down. They don't ever point sideways. So the x component of the vector is always 0. And the y component is absolute y. So the y component is always positive, or I suppose non-negative. It's always pointing up. And the further away from y equals 0 they go, either upwards or downwards, the more up the vector points. So when we're down here way below y equals 0, the vector points up a whole lot. And the same when we're up here way above y equals 0. Okay, so let's try to compute these then. The divergence of x, well, dp dx is 0, plus dq dy is 0. In the curl, we have dq dx as 1 minus dp dy is 0. The curl happens to be 1 everywhere. And that is positive, as we expected. And then looking at part f, our curl of f, well, that's dq dx, there's no x's there, so that's 0, minus dp dy, that's 0. Our curl is 0, as we expected. The divergence of x, the divergence of f, well, dp dx is 0. But then what's the derivative of absolute y? Well, it's kind of like plus 1 when y is bigger than 0. Right? When y is bigger than 0, absolute y is just y. So this would be like 0y for positive y's. So our y partial will be plus 1, but 0 plus a negative 1 for y less than 0. When y is less than 0, absolute y is just negative y in that case, the derivative being negative 1. So our divergence is positive when y is positive and negative when y is negative. That was what we expected. So we can get an intuition as to how the curl and divergence are working in at certain spots in a vector field by looking at these circles and its flow going in or out on a net basis, and by looking at these like weather vane kind of things and seeing, is there a tendency to make them rotate counterclockwise or clockwise for the curl? And then we can actually compute those results using these definitions. And again, I want to just reiterate the fact that typically, if you just have an arbitrary vector field, your divergence and curl are going to be functions of x and y for both of them. And they're going to be different values depending on what x and y point you're looking at. They could even be changed sign completely for different points. We just pick some easy to evaluate ones here. So that's why all of our results happen to just be numbers. But these are like kind of, in a sense, constant vector fields with respect to curl and divergence for the ones that we picked here. Okay, so let's take a look then at what happens when we jump up to 3 dimensions. Well, let's skip over curl for a second. The divergence is exactly what we'd expect. The divergence of f is just, where f is PQR, is just dp dx plus dq dy plus dr dz. Simple. Curl f, though, all of a sudden gets kind of crazy. I note that curl f, number 1, is a vector quantity. It's something times I plus something times j plus something times k. I also notice that I have kind of all of these partials that have to be taken into consideration. Let's first ask ourselves, why should curl in 3 dimensions be a vector quantity? Well, in 3 dimensions, maybe I have a tendency for my field to kind of rotate this way. I guess that could be the case, like rotating horizontally. But kind of for an arbitrary field, it might have a tendency to rotate, and I'm probably going to do a terrible job at drawing this, but it might have a tendency to rotate in some funky direction like this. It's not really horizontal or parallel to the XZ plane or parallel to the YZ plane. It's kind of in some like skew plane here. It's not really a plane that's the plane of rotation is not really a plane that's parallel to any of the three coordinate planes. Maybe that's where this kind of little vortex is, this kind of little tendency to rotate. So I actually have to describe this with a vector that's in kind of some sense normal to this surface of rotation. That's how I say what direction it's rotating in. I can't just say whether it's positive or negative because now that I have 3 dimensions, I can tilt it all kinds of different ways. If you've ever done anything with, say, torque in physics or anything like that, it's a similar idea. So like the torque vector is like if you're turning a wrench, you have some screw like this, and you have a wrench attached to it, and you're turning a wrench this direction. The torque vector is like in that direction. It's in the orthogonal direction to the plane that you're turning the wrench. And so torque has to be like that because that's how I kind of tell what plane you're turning the wrench in. We maybe saw a short example of this all the way back to the beginning of the course when we talked about cross products. The torque looks like the cross product of some things, and the cross product, of course, is perpendicular to the 2 inputs. So that's the reason that curl has to be more complicated in 3 dimensions. Why doesn't it have to be complicated in 2 dimensions? Well, because we're always either, well, if we're rotating counterclockwise, we take our right hand and we curl our fingers right to left and our thumb points out of the screen. Or if we're going clockwise, we kind of, you have to manipulate your arm a little bit, but curl your fingers the other way and your thumb points into the screen. You can only point out of the screen or into the screen. You can only point in, say, a positive direction or negative direction. So the sign, positive or negative, is enough to tell you which direction you're pointing when we only have a 2-dimensional field. In a 3-dimensional field, there's all kinds of wonky angles you could be at, so we need more than that. We need a vector. This is a vector in R3. The divergence is just a scalar, as it was before. It's just a number. So really what we defined up here when we said that this is kind of like, or we said this is kind of the curl, and it wasn't really the curl, because the curl really is kind of this vector quantity. So this is something like a 2-dimensional analog of the curl. It turns out that the curl, I think I mentioned down here also, but the curl is really kind of fundamentally a 3-dimensional thing. Most of the things we've talked about so far, we could generalize them. They would work just as well in 2 dimensions or 3 dimensions, or in theory in 4 or 10 dimensions, maybe harder to draw, but we could apply basically everything we've talked about to higher numbers of dimensions. The curl doesn't really generalize in a natural way from 3 dimensions, either down to 2 or up to higher dimensions. So people have come up with generalizations of it, but it's kind of fundamentally a 3-dimensional thing. Kind of how the cross product is kind of fundamentally a 3-dimensional thing. But the divergence, generalizes very nicely to 2 or more than 3 dimensions. We just lose or gain some partials onto it. Okay, so divergence isn't that hard to remember, but curl has all of these crazy partials with minus signs, so we even got to get the order right and everything. So how do I remember the formula for curl? So let's take some notation. We denote the differential operator, this nabla here, as the vector consisting of differential operators. The first component is the partial with respect to x, not the partial of something with respect to x, but just the operator that's partial with respect to x. second component partial with respect to y, third partial with respect to z. We can then kind of symbolically act this operator on a vector field to get something like, and I have, well, to get something like this, something like grad f equals nabla hitting f, where we kind of apply this component wise. Again, gradient really takes in a scalar function, so I'm being a little bit loose here with the notation. But we can think of something like this. But the main things that we want to look at are these two that we've introduced here. Curl f, the curl of a vector field, turns out to be, if we think of this as a vector and our field is defined by a vector, we can take this vector cross f. What do we mean by that when we say something like that? Well, what I mean is when I take the cross product, I take the determinant of ijk, then the three components of vector 1, then the three components of vector 2. So I take the determinant of ijk, partial with respect to x, y, and z. I can't really easily select this middle row here without selecting the whole thing. And then in the third row, p, q, and r, the three components of our vector field. We'll go through an example and we'll see how this actually works out in practice. You might say this looks a little wonky. Can we actually do this? And the answer is, well, kind of yes and kind of no. Kind of yes, because it actually works out pretty nicely, and maybe we can make some more abstract arguments, and kind of no, because, well, I mean, this isn't actually a vector, so taking its cross product of it with something doesn't actually, it makes sense in terms of the definitions that we've laid out. But there's a wonderful quote by statistician George Box that all models are wrong, some models are useful. We might look at this and balk it and say it's wrong, but it's certainly useful because I really don't want to memorize this whole thing. So we'll see how it is used in a second here. And the divergence is like grad dot f. It's like the dot product of this vector with this vector. I multiply, in a sense, or I apply partial with respect to x to the function p, partial with respect to y to the function q, partial with respect to z to the function r, and then I add them together, and that's exactly what my divergence is. So again, note one is just really saying, what do we mean when we say something like this? It's a little clear what we mean when we say something like this, but a little less clear there. Note two, we can recover this 2D analog of curl by first taking our two-dimensional vector field and kind of appending a third dimension onto it, but just making that 0. So just making a three-dimensional vector field where all of the k components are just 0. So we just smush it back down to 2 dimensions. And then we note that curl f here, we can do the work. R in this case would just be 0. Let me just type it in there for 1 second, and I would see that, for instance, I times partial with respect to y of 0, well, that's 0, and then minus partial with respect to z of q, but q doesn't depend on z, so that's also 0. So we get I times 0, we would get j times 0 as well, and we would get k times what? Partial with respect to x of q. That's what I have here. And then minus partial with respect to y of p, and that is what I have there. So it all works out. Let me put the r back in there. So if I define, so I see that curl f equals dq dx minus dp dy times k. That's the vector that's pointing out of the screen or into the screen. And then I could say that, well, curl f dotted with k, that's just this number times k dot k, but k dot k is just 1. that's just length k squared, which is just 1, is dq dx minus dp dy, or that's kind of a little bit like the length of the curl of f, right? It's plus or minus the magnitude of the vector that's the curl of f. So it kind of is like the curl, but it also kind of isn't like the curl, because if it was really a curl, I would expect that for a two-dimensional vector field, I would expect to get a two-dimensional vector out, and that's what I would really want to call the curl. But I get either something that's like a one-dimensional vector or that's like a three-dimensional vector, depending on your perspective on it, but it's certainly not a two-dimensional vector. So that's why I was saying that it's a little wonky when we try to move the curl from 3 dimensions down to 2. We do get kind of an idea that seems to work. In fact, that's where we developed our intuition. But it's not exactly, it doesn't exactly have the same properties as the actual curl. So it's this thing that's a two-dimensional analog of the curl. And I mentioned this already a couple of times. Okay, so in example 3, let's compute the divergence of this vector field f. First component e to the xy, second component x times y, third component z to the fourth. We want to compute this at the point 1, 0, 2. So the divergence of f, which we could write in the notation grad dot f, is the partial with respect to x of the x component. Well, that's e to the xy times d by dx of xy, which is just a y, plus partial with respect to y of the y component, d dy of xy is just the constant in terms of yx, plus d dz of the z component, d dz of z to the fourth is 4z cubed. This function, this say g of x comma y comma z, is the divergence of f. As I said, generally speaking, the divergence and curl are going to depend on x, y, and z, or x and y. It's going to depend on what point in the field you're looking at. You're going to get different values. And that's the case here as well, right? We can see very clearly if we picked y and z to be 0, when x is positive, the divergence is positive, and when x is negative, it's negative, and when x is 0, it's 0. So we can see very clearly that in different points of the field, we can get a positive or a negative or a 0 divergence out of here. So our simple examples before were just simple examples, and these ideas are in general local properties. So the divergence of f is this function of x, y, z, and the divergence of f evaluated at 1, 0, 2 is what? Well, y is 0 times whatever is 0, plus x is 1, plus 4 times 2 cubed. So that's 4 to the 5th is 32, and 1 is 33. So mechanically, not a very difficult thing to do. Just take 3 partials and then evaluate if you need to. But the conceptual things, are where some of the hiccups can happen. That the divergence takes as input a field, gives as output a scalar function that we can evaluate if we want to. And this is saying that at the point 1, 0, 2, that's acting like a source. It seems like there's more field flowing out of that point than flowing into it. If we're thinking of a gas, maybe the gas is heating up or expanding there. If we're thinking of a fluid, maybe there's a pipe there. But I suppose gas is a fluid. If we're thinking of a liquid like water, maybe there's a pipe around that point that's putting more water into that area. It's a source. So water's flowing kind of out from that three-dimensional point. Okay, let's look at this vector field, a different one. We want to evaluate the curl of this vector field at the point 1, 0, 2. Okay, so again, I mean, I guess I could memorize or write down somewhere all of those partials and with the negatives and all that, but if I get even one minus sign, two of the terms flipped, I'm going to be off. So I always think of curl as grad cross f. Right. You probably shouldn't say grad cross f. I just always say it that way. Should probably say something like nabla cross f or maybe del cross f, something like that. But I always tend to just say grad when I see the gradient symbol. That's probably not quite the correct way to say it. So if I'm taking a cross product of two quote vectors, my first row is ijk, my second row is the first vector, which in this case is like partial with respect to x, partial with respect to y, partial with respect to z. Again, is this really a right thing to do for a cross product as we defined it? Maybe not, but it works, and it's a good mnemonic device, if nothing else. And then what is my vector f? Well, that has three components. The first is xy, the second is e to the x, and the third component is y plus z. All right, so here we have I hat times. What would we normally do? We would go down this diagonal, multiply these things. But instead of multiplying, I'm just going to apply the differential operator to the function. I'm going to take partial with respect to y of y plus z. Then I will do minus, taking I hat and going the other direction. With two kind of standard vectors, I would multiply these, but here I'm thinking of applying a differential operator to a function. I apply d dz to e to the x. And then plus j, well, j going the top left to bottom right direction gets a d dz of xy. Well, that's d dz of xy is 0 minus j gets it's a little strange the way I wrote it here, but j hits d dx times y plus z. Again, that's not really a times, it's an apply the partial with respect to x to y plus z. That's also 0. And then plus k, it wraps around top left to bottom right. d dx of e to the x is e to the x minus going top right to bottom left, d dy of xy is x. So the curl of f turns out to be the vector function. d dy y plus z is just 1 minus d dz of e to the x is 0. First component is just the number 1 or the function 1, I suppose. For any x, y, z input, any point we input, we get the output 1. The second component is just the function 0, the 0 output for any input. And the third component, e to the x minus x. So in this case, the curl is a vector that has x component 1, y component 0, and z component e to the x minus x. So the direction of the vector, the plane that the kind of pointwise rotation is happening in, the tendency to rotate it is happening in, really is only dependent on the x coordinate of that point, and really it's only the z component of that normal vector that's being affected. And then what's the curl of f at the point 1, 0, 2? Well, that's first component 1, second component 0. I didn't actually plan for these both to be 1, 0. It's just a coincidence that the first two components of the curl are 1, 0, and the first two coordinates of the point are 1, 0. I didn't really notice that until now. And then my z component is e to the x minus x, or just e minus 1. So that's kind of like the vector that's pointing normal to the way that I'm kind of instantaneously tending to rotate at this point. My plane of rotation would be the plane that's normal to this vector 1, 0, e minus 1. Okay, so let's look at, I put some properties here, but just really just a property of each of them. Something we have to be very careful with when we're dealing with these vector calc ideas is what are the inputs and what are the outputs. So again, I was a little sloppy when I kind of wrote something like this up here. So the gradient, or just applying the differential operator directly to a function, takes as an input a scalar function, a function that has one output, and it yields a vector field. It yields the gradient vector field that's a three-dimensional field. Here we're just dealing with R3 so that the curls and cross products all work out okay. But if we forgot about the curl, we could make these Rn and it would be just fine. The divergence takes as its input a vector field, say a three-dimensional vector, and gives us its output a scalar function. Right, took as input a vector field, gave as output a scalar function for the divergence. And the curl takes as input a vector field, a three-dimensional vector, and gives as output also a three-dimensional vector. So our book doesn't, our book goes into this a little bit, but not all the way. But we're going to do a little exercise here. This looks like a lot of work, but it shouldn't be too bad. So if I wanted to combine derivatives, I kind of have like three different types of derivatives: gradient, divergence, and curl. If I wanted to combine them to get something like second derivatives, some of the combinations make sense and some of them don't. If I try to plug a vector field into a gradient, well, that doesn't really make sense. I can't take the gradient of a vector field. So I can't, for instance, take the gradient of the curl of a vector field. So let's look at these. Let's go down the list and see which ones make sense and which ones don't. And for the ones that make sense, we'll investigate them a little more. Does it make sense to take the gradient of a gradient? Well, the input is a gradient, which goes from 1 to 3 dimensions. And I'm trying to plug that into something that wants to take as its input a one-dimensional. So do these inner dimensions match up? Well, no, they don't. I'm trying to plug the output of this gradient. I'm trying to plug a vector field into a gradient, and a gradient can't take a vector field as its input. So I'm just going to put a big X through that one. We can't really take the gradient of a gradient of, say, a scalar function. That wouldn't make a lot of sense. Can I take the gradient of a divergence? Well, divergence takes a vector field as input and yields a scalar function, right? The sum of the three partials. What am I trying to plug that into? I'm trying to plug that into the gradient, which wants to take a scalar function and make a vector field. The inner dimensions actually do match. My divergence gives as output a scalar function, and that's what the gradient wants to take as input. That works. So this actually is valid. So the divergence is px plus qy plus rz. This is some function, let's call it g of x comma y comma z. I can take the gradient of this function. It's just some function of x, y, z. Just because it happens to be the divergence of some vector field doesn't matter. It's just some function of x, y, z. I can take its gradient what does that say? It says take the x derivative. So take the x derivative of this function and make it my first component. So I guess I would get like pxx plus qxy plus rxz in my first component, and so on. Not a super nice result, but I can do it. I can take the gradient of the divergence. Can I take the gradient of a curl? Well, a curl takes as input a vector field and gives as output a vector field. But gradient wants a scalar function as input. It doesn't want a vector field. No, I can't do this. Can I take the divergence of a gradient? A gradient takes a scalar function in, gives a vector field out. A divergence takes a vector field out. Sorry, I think I said that. A gradient takes a scalar function in, gives a vector field out. A divergence takes a vector field in, gives a scalar function out. The insides match, so the gradient, the vector field coming out of it, can be plugged into the divergence, which wants to take as input a vector field. What do I end up getting? Well, I put into this whole thing a scalar function, and I end up getting out a scalar function. So if I have grad little f, that's fx, fy, fz. And then if I take the divergence of that, if I take the divergence of this vector field, which will be a gradient vector field, I take the x derivative of my first component. To that, I add the y derivative of my second and the z derivative of my third. This is actually a really nice and important function. This is called the Laplacian. Sometimes as a shorthand notation, we write grad squared little f for this. Or more often we write kind of delta little f. Sorry, there are so many triangles pointing different ways, but this is called the Laplacian of f. And it's an important idea in, say, partial differential equations and a lot of different areas. But this is a legitimate thing to do. Can we take the divergence of a divergence? A divergence wants to take as input a vector field and give as output a scalar function. Can I plug that into something that wants to take a vector field as input? No, I cannot. Can I take the divergence of a curl? A curl wants to take as input a vector field, give as output a vector field. I'm trying to plug that into a divergence, which takes as input a vector field and gives as output a scalar function. That works. The output from the curl is a vector field, and that's what the divergence wants to take as input. So overall, I should be inputting a vector field and getting out at the end of all of this a scalar function. What would this be? Well, grad cross f is, I'm gonna cheat here and just copy. So that's grad cross f, that's this bit. I want to take the divergence of this. In other words, I want to take the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. Well, the x component is ry minus qz. I want to take the x derivative of that. That's rxy minus qxz. I'm assuming that I can flip the derivatives around. Plus the y derivative of the y component, pyz, minus rxy plus the z derivative of the z component plus qxz minus pyz. But hey, wait, pyz minus pyz, qxz minus qxz, rxy minus rxy. This always equals the scalar 0. The divergence of the curl is just the number 0, so long as our functions are nice enough that we can flip the derivatives around. So this makes sense to do, but it just always gives us a 0. Okay, so what else do we have? Well, can we take the curl of the gradient? The gradient takes a scalar function in, gives a vector field out. Can I plug that into the curl, which wants to take as input a vector field and give as output a vector field? Yeah, sure, I can. So for this one, I'm going to leave this as an exercise because we're running short on time. As an exercise, show that this always equals the 0 vector. It's not that bad to do. But remember, the curl, what we're getting out is a vector field. This vector field will always be the 0 vector field. It'll have 0 in each of the 3 components. So we can do this. This does make sense. But again, always gives us a 0 vector. What about the curl of a divergence? A divergence wants to take as input a vector field, give as output a scalar function. A curl wants to take as input a vector field. These are not the same. I would be trying to put a scalar function into a curl. Can't do that. And then what about the curl of the curl? The curl takes as input a vector field, gives as output a vector field. I want to put that into a curl, which takes as input a vector field, gives as output a vector field. That does make sense to do. I can keep taking curl of curl of curl of curl of whatever. It turns out that this isn't, so we can do this. It's not super nice. We don't get a nice result like the zeros here or like the Laplacian up here. It's actually kind of related to this part B idea. So related to part B, they're both kind of messy formulas, and they kind of they have some relation to something that's kind of like a vector triple product. There are some relations between them, but kind of long story short, B and I, these two ideas, just not super nice formulas. But we could do it. Okay. So next up, a theorem. F is a conservative vector field if and only if the curl of F is 0 everywhere. So for a proof, let's prove this direction first, that if F is a conservative vector field, then curl F is 0. So F is a conservative vector field means F equals grad little f for some little f. But wait, curl of big F is the curl of the grad of little f. But the curl of the gradient is always the 0 vector. A corollary of this is, so we're saying if F is conservative, then curl F is the 0 vector. The corollary is the contrapositive. If the curl of F is not the 0 vector, then F is not a conservative vector field. So we have another test for a conservative vector field. If we happen to compute or to know the curl of a vector field, and if it's not 0, then we know that F is not conservative. For this direction of proof, to prove that if the curl is 0 everywhere, then F is a conservative vector field. We really can't do this at this point, but this is a consequence of Stokes' theorem. It has a little bit of the feel to me of like how Green's theorem helped us prove the partial derivative test for conservative vector fields. It has a bit of that feel to it, which we would expect because this curl, right, it looks a heck of a lot like that partial derivative stuff that was inside of Green's theorem, which is where the partial derivative test kind of came from. So linking all of these things back together doesn't seem like such a strange thing. So the other direction can be proved by Stokes' theorem, and if we have time in the lecture, we'll point out how that would come about. It would look fairly similar to the Green's theorem example. Okay, and then the last little topic here, we have two restatements of Green's theorem in vector form. These will be restatements that will kind of make it look a little bit more like the Stokes and Divergence theorem that it's related to coming up here. Well, part A, we can easily see that the line integral of FDR, which is defined to be this, by Green's theorem, this should be the double integral over D, a domain of Qx minus Py dA. But of course, as we mentioned before, where was it? It was in my note up here, if I can find it. There we go. Curl F dot K is just exactly that, Qx minus Py. So this Qx minus Py, the stuff from the inside of the integral in Green's theorem, is just curl F dot K. So if we think about this, kind of what this is doing is it's looking at around our curve at some point. We have like a tangential component. Remember, F dot dr is kind of like F dot t ds. It's like the tangential bit. We have kind of a Green's theorem for the tangential stuff. But then we can also think of a normal to this curve here, and I'll write it maybe as an n hat because we're going to take it to be a unit normal. I have an outward normal that's the normal meets the tangent vector at 90 degrees, and it's outward because it's pointing outside of the interior domain here. It's pointing away from that central bit. So I have a tangential bit that's kind of what I've looked at in part A, and I have a normal bit that's what I can look at in part B. And here I'm just the details are in the book and we're running out of time, but I'll kind of quickly sketch the proof. And when I try to do things quickly is usually when I make mistakes. So I'll try to stick closely to my notes here. Our unit tangent vector is x prime over length r prime, y prime over length r prime. I don't think any of this is really novel. Perpendicular to our unit tangent vector, we have to get it in the right way, but it turns out that our normal is going to be negative y prime over length r prime, positive x prime over length r prime. So that's our unit normal. We just swap the x and y coordinates and make one of them negative, and we do it in such a way that the normal points outward. Then the line integral of f dot n dr is the integral a to b f dot n length r prime dt, and this is the integral a to b of py prime minus qx prime. Again, I'm skipping a lot of the explanation here because we're about out of time. We are out of time now. And y prime dt is dy, x prime dt is dx. This is integral a to b of p dx plus, plus q dy, or again, I'm skipping, so I'm making a couple of mistakes here. PD, how did a y turn into triangle? PDY minus q dx. And if we apply Green's theorem here, we have P and Q are swapped a little bit in this version. So to apply Green's theorem, we have to make a little bit of a change. This is the double integral over d of px plus qy dA, which is the double integral over d of the divergence of f. That's a scalar function, so it doesn't need to be dotted or anything like that. Divergence of f dA. The details are in the book. I rushed through it because we're out of time, but this is just kind of applying Green's theorem, but we have to kind of swap around some of the P's and Q's from our normal statement of Green's theorem. And the main thing was to make sure that this normal points outward just to get the sign in the right place. But okay, so that wraps up our discussion of curl and divergence. Again, supplement on 16.6 coming out. Wednesday's class 16.7. Next week, our final week of the class, of the course, Stokes' theorem on Monday. Supplement on divergence theorem also posted on Monday. And no class meeting on Wednesday. We're allocating that time to the exam. All right, I will see you all on Wednesday. Have a good one.